Okay, so another presentation class in power engineering. So this is the third part of the presentation in cooling tower. So this presentation tackles more on the additional examples given in order for you class to be uh, familiar with other applications of cooling tower. Okay? So another example, an atmospheric cooling tower is to provide cooling for the jacket water of a 4-stroke 1,000 kilowatt diesel generator set. So this is a 1 megawatt generator set. So the cooling tower efficiency is 60% at a temperature approach of 10 degrees. Okay? If ambient air has a dry bulb temperature of 32 and 70% relative humidity, determine cooling water supplied to the diesel engine in liters per hour. So the generator efficiency about 98%. Okay, so class, so this is the given. So the combined power is 1,000 kilowatt, approach is 10, cooling tower efficiency is 60, the dry bulb temperature is 32, the wet bulb temperature is 27.4, generator efficiency of 98, brake thermal efficiency of 30, and the heat carried by the jacket water is 26%. Okay, so let us now come to the solution of this. Okay, so the mass of makeup water. So knowing that the approach is equals to the temperature, of course, of the entering water, of the living water rather, multiplied by the wet bulb temperature. Okay, substituting this uh, to the formula for cooling tower efficiency, and then the temperature of the living water now is 37.4 degrees Celsius. Okay, so or TV, yes, TV rather is 7.4, and then getting TA now. So TA, or the temperature of the water entering the tower, is 52.4 degrees. And then getting the brake power, knowing the thermal efficiency and the combined, or the generator efficiency rather, and the combined power, the brake power now is 1020.41 kilowatts. Okay? So, again, getting the energy chargeable, knowing the thermal efficiency of 30%. So, energy chargeable now is 3,401.37 kilowatts. And then, getting the heat carried by the jacket water, that is 884.36 kilowatts. Okay? So, getting now the mass flow rates in liter per hour, the answer is 50,652 liters per hour. Okay? So, take note, class, that the heat carried by the jacket water can be equated by the mass multiplied by the Cp and the change in temperature of the jacket water. Okay? So, another example, a mechanical drop cooling tower receives 150 cubic meter per second of atmospheric air at 101.325 kilopascal and 32 degrees Celsius. So, and then 55% relative humidity. And discharge the air at saturated. Okay? So, 100% relative humidity meaning. Okay? So, at 36 degrees Celsius, if the tower receives 210 kilogram per second of water at 40 degrees Celsius, what will be the temperature of cold water? Okay? So, the given class is, of course, the initial temperature of the water is 40, and then mass of water is 210 kilogram per second, and the volume of air is 150 cubic meter per second. Okay. So, from the data of the saturated air, so at 36 degrees Celsius, saturated, so from psychrometric chart, the value of the enthalpy is 135.56 kilojoules per kilogram. And then looking now at the right portion of the psychrometric chart, the humidity ratio now is equals to 0.039 kilogram water per kilogram of dry air. And another at 32 degrees and 55% relative humidity, again from psychrometric chart, the enthalpy now at 1 is 99.8 kilojoules per kilogram. And then again, looking at the right portion of the psychrometric chart for humidity ratio, the value is 0.0265 kilogram water per kilogram of dry air. Okay? So, getting now the temperature at 2 or the temperature of the cold water from the formula of ideal gas equation or the ideal gas or ideal gas equation or equation of state. So, PV is equals to MRT or density is equals to P over RT. Substituting values, knowing that the pressure is 101.325, the gas constant for air is 0.287 kilojoules per kilogram Kelvin, and then the temperature of air is 32, getting the absolute, plus 273. The density of air now is 1.158 kilogram per cubic meter. Okay, so getting now the mass. Knowing the density. Density is equals to mass over the volume. Okay? So, the mass now of air is 173.7 kilogram per seconds. Okay? So, take note that the heat carried by the cooling water is, or heat carried by the cooling water is equal to the heat absorbed by the air passing through the cooling water. So, we can equate now that 2. Okay? So, and then getting now, or knowing that the mass is 210, and then specific heat of water at constant pressure is 4.19, the initial temperature of water entering the tower is 40, and the temperature of cold water is unknown, and then the mass of the air is 173.7 multiplied by the change in enthalpy. Therefore, the temperature now of water leaving the cooling tower is 32.96 degrees Celsius. Okay? So, this is easy. Okay? Another, a cooling tower receives 10 kilogram per second of water at 60 degrees Celsius. Air enters the tower at 32 degrees Celsius, 28 degrees centigrade with bulb, and leaves at 45 degrees. Okay, 90% relative humidity. Cooling tower efficiency is 60%. Determine A, mass flow rate of air and kilogram per seconds, and B, quantity of makeup water required in kilogram per second. So again, given is the initial temperature is 60, and the T sub 3 or the temperature of water is, or of the air rather, is 32 degrees dry bulb, or dry bulb rather, and 28 degrees wet bulb. Okay, so, and then the exit, that is 45 degrees Celsius and 90% relative humidity. And the cooling tower efficiency is 60%. Okay, so getting now the temperature of the living water. So, substituting values from the cooling tower efficiency formula, T sub 2 is 40.8 degrees Celsius. Okay? So, take note again that the heat carried by the cooling water is equals to the heat absorbed by the air. So, take note, at 32 degrees, saturation pressure is 4.79886 kilopascal. And at 45, the saturation pressure of air is 9.5934 kilopascal. So, getting now from the formula for humidity ratio. So, humidity ratio now is 0.622 multiplied by the saturation pressure of air divided by the atmospheric pressure minus the P saturation. Therefore, the humidity ratio now at 1 or of the air entering the tower is 0.0309 kilogram of water per kilogram of dry air. Okay? So, next. So, let us now take for the humidity ratio of the living air. So, again, from the formula for humidity ratio, 0.622 multiplied by the partial pressure or the P saturation rather, 9.5934 over the atmospheric minus the P saturation at 2. And then the humidity ratio now is equals to 0.065. This is not W sub 1 but W sub 2. Okay? So, I'm sorry. So, that is 0.065 kilogram of water per kilogram of dry air. So, let us now consider the formula for the enthalpy. Okay? So, the enthalpy now of the air is equals to Cp multiplied by the temperature plus the humidity ratio multiplied by the enthalpy of water. Okay? That is now equals to 1, the Cp, of course, multiplied by 32, the temperature. Okay? Plus 0.0309 multiplied by the 2559.84. So, the enthalpy now, of course, is 111.099 kilojoules per kilogram. Same as for the enthalpy of the living air. Okay? So, that is at 45 degrees. So, the substituting values now, the specific heat is 1, the temperature is 45 plus 0.065, the humidity ratio plus or multiplied by the H sub G at 45 degrees, which is 2583.32. Therefore, the value of the enthalpy of the living air is 212.908 kilojoules per kilogram. Okay? So, again, equating again the formula, the heat carried by the jacket water is equals to the heat absorbed by the air. Substituting values, mass of water is 10 kilograms per seconds, and then specific heat of 4.187 or 4.19 multiplied by the change in temperature of 60 minus 40.8, and then mass of air is equals to multiplied by the change in enthalpy of air. Mass of air now is 7.89 kilogram per seconds. Okay? So, also, mass of water is equals to the mass of air multiplied by the humidity ratio or the change in humidity ratio. So, that is equals now to mass of water is equals to 0.27 kilogram per second. So, this is now the make-up water required. So, in order to replenish the water carried by the air as it passes through inside the cooling tower. So, 0.27 kilogram per second. Thank you very much, class. That ends now my presentation. So, this is the last part of the presentation in cooling tower. Thank you very much.